welcome everyone to this fifth presentation in the series Forging Ahead. And we are forging ahead in mathematical logic. We have presented fundamentals, we have presented the splendid theorems of Kurt Gödel. Gödel had even more splendid theorems than I was able to present. But we are now moving to logic where it's about to be in 30 minutes. We are moving mathematical logic forward. In 30 minutes, you will have your experience with well-structured mathematical logic, and that is the substance of today's presentation. Also, I hope I have prepared you for it in the fourth presentation. Let's get to work. Being thoroughly structured is not the same as being well-structured. Many people believe that the traditional formalization of mathematical logic is already well-structured. This is not so. Even though the formalization is structured, and even thoroughly structured, it is not well-structured. It gives rise to forms that are relentlessly nest-knotted and user-hostile, as anybody who has worked with this stuff knows all too well. Context-oriented mathematical logic is not just logic done in a new way. It may well be logic as it always should have been. Contrary to conventional wisdom at the current time, machine-parsably formal systems do not have to be relentlessly user-hostile. We will show how the new formal linguistics can be used to create a system in which formal logic can be made to fall into pliant, easygoing, user-friendly forms. In the well-structured system, the machine-parsably rigorous calculus for this logic also becomes pliant, easygoing, and user-friendly. Though we cannot show you the pliant, easygoing nature of the calculus in this 30-minute glimpse of logic. Now, we review. To get to the next mountain ridge, you must cross a deep valley. We lost a lot of elevation on the fourth presentation so that we can now start climbing up onto this next mountain ridge. The ridge you're on, assuming you're doing traditional logic, when formalized in traditional formal logic, properly called Frege-Hilbert syntax, mathematics is indeed machine parsable, but it is relentlessly, hopelessly user-hostile and unworkable. Now, people who do mathematics don't realize the utter unworkability of traditional formal logic. Just yesterday, I was looking through this marvelous presentation by Walter Rudin, marvelous expositor. It was not user-hostile, but it was not machine-parsably rigorous either. To get to machine-parsable rigor in the current age, you have to suffer through hopeless user hostility. But on the next ridge over, look at what happens. When formalized in well-structured mathematical logic, mathematics still becomes machine parsable, but it is also user-friendly, pliant, and easy. The new formal linguistics provides the way to the next ridge over. Syntax can be nested in three different ways. Nested syntax falling inside other syntax, as is very, very familiar. Flowing, syntax flowing after other syntax, such as matrix multiplication, or for that matter, the notes in a melodic line. We already are outside of universal grammar, having a structure of syntactic expression that's not all nested. Then random access is also a phrase structure. The syntax is jumbled together, such as matrix addition. All three methods of phrase structure ramify with themselves and with one another to yield diversified ramification. In general, flowing and random access structures are user-friendly, but nested structures are user-hostile, as a whole chapter of that book goes at great length and labor to demonstrate. Implicit phrase structures need to be discussed. There are phrasings and nestings and flowings of phrasings in prose, in poetry, in informal exposition of mathematics, and so forth. Being, if you get into phrase structures, much as the author of this book does, you can see these phrase structures even if they are not explicitly written. In practice, both on the ridge you're on and on the next ridge over, one may suppress notation of phrase structure when it is algorithmic to put the phrase structure back in. Still, the phrase structure is every bit as much real and there, even when it is implicit. That is, when it is not written out. And I should have suppressed, I'm making derogatory comments. Oh my word, I was supposed to have deleted them. Well, I'll read it anyway. Once this observation is seen, one realizes that Polish notation and reverse Polish notation are relentlessly nest-oriented and consequently user-hostile, even if the notation of writing these nests is suppressed in those systems. The new formal linguistic also provides the means for looking critically at the formalization of Gensen and others who have sought to bring user-friendliness to formal logic, and I don't think they succeeded. So, well. The central result of the new formal linguistics informs one exactly where one can place flowing and random access phrase structures into a newly composed formal language. It also tells where one cannot place such structures, and thus where one must employ a nested structure. By making greatest use of the flowing and random access phrase structures, which are user-friendly, one may maximize user-friendliness into a newly composed formal language. Throughout all this material, as I've said before, all details can be found here in this book. Let's rephrase first-order logic. The methods of theory of phrase structure the book presents can rephrase computer programming languages, and one of its chapters does. You can rephrase a lot. Let's rephrase first-order logic. It will only take a few minutes if we just rephrase the language and not logical deduction and proof. So as to ensure that phrase structure is clear, all notation of phrase structure is written out. Nested structures are indicated with parentheses or brackets. Flowing structures are indicated with a comma. Random access structures are not explicitly used in the new formalization. They show up as rules of calculus, in fact, as commutativity rules. And nor I nor the author of this book, who are the same person, has thought up a separate notation for random access phrase structure, though it's fully justified by the theory. We rephrase absolute truth and falsehood. On ridge you're on, 0 stands for Boolean falsehood, and 1 for Boolean truth, as in a computer language. In the next ridge over, we use a sans serif dialect. Semicolons make 1 point of phrase structure work out later, which will not even be covered in this glimpse. Absolute falsehood means this, and absolute truth for that. And there you have it. It doesn't look like we're making much progress onto the next mountain ridge, but we're doing something. In the ridge you're on, negation introduces a nest level. Not P is phrased like that. In the next ridge over, negation flows with the statement being negated. This causes cognitive dissonance for many people. Get over your cognitive dissonance. The author of that book, which is the same as the presenter before you, has worked it all out by the theory of phrase structure that this works. Dad, stop. Oh, please. Oh, oh. Oh, my word. There. Okay, what's that? We have here the semantics of non. We rephrase the binary Boolean operators we put at the ground basis, fundamental basis, if then and rather than the traditional or and you'll get the same logic anyway. But this is how the phrase structures work for if then and. On the next bridge over, we have given and required. When given a statement P, Q happens. When required a statement P, Q happens. The brace sets and comma are very carefully set in place. We now eliminate the last argument as before, and we have this and that as hungry functions on the space of statements. We have these semantics which ramify by scale of expression. At small scale, this G thing means if P. The R thing means then, that should be actually a key over on this, no, then P. Over here in middle scale, assume P is true. We show P is Q if it's on an R clause. Or we have shown P is true. This tense of the verb depends on the aspect of the clause, which you cannot even get a glimpse of in this 30-minute presentation. At large scale, a G clause means take as an axiom, let it be postulated P. And at large scale, an R clause means theorem or proposition P. Now, people have noticed that if, assume, and axiom have a lot of the same meaning, but this is now completely formalized and extends. We rephrase the quantifiers. In the ridge you're on, you have for all x, Q is put in a bracket set in traditional formalizations. In the next ridge over, we again change the phrase structure. The variable x is encapsulated in a brace set. The concluding statement is out in the open, and it flows after the quantifier. The semantics do ramify by scale of expression. At small scale for all x. Let x at middle scale. Let, by definition, x be this meaning for the rest of this branch of mathematics at large scale. Over here, for some x, make x, which is hard to tell the difference between making and letting, but that's just how it goes. And make, by definition, x have this meaning for the rest of the branch of mathematics. It's getting a little, you're starting to see the system starting to do things that you yourself don't even see yet. Okay? It's having a life of its own, making things happen. We rephrase and reconceive of the such that operator. Traditionally, the such that operator is just filler for the there exists construction. On the next bridge over, such that is a first class operator. It works in conjunction with the quantifiers to produce qualified quantifiers. Here are two examples. For all real numbers x, so that x is positive. Here's another one. There is, for some real number delta, so that delta is positive. And if you concatenate this and that together, you're using the constructive form inside context, that they just flow, and that's how that works out. The succeeding statements or main clauses have already been eliminated. Those who were here for the fourth presentation are accepting, I hope, these lines as fully existent on their own. Takes a bit of doing, but you can do that. We do not rephrase the substitution operators. We're sorry. Lack of time does not allow this to be shown in your 30-minute glimpse. They occupy a full chapter of that book. Now, we're going to examine a specimen actually for the rest of this presentation, the mean value theorem, and it is a mean value theorem. This presentation is called informal by us mathematicians or mathematical logicians. An English teacher would say this is darn formal presentation, but for us it's informal. Let f be a function with real inputs and real outputs, and let a and b be real numbers with a less than b. Assume that f is differentiable throughout this interval, and assume that f is continuous at a and at b. Then there exists this real number. I'm going to stop the presentation right now And when I return, I'll have a diagram on the board, since some of you might not know this theorem very well. I'm back, and so are you. So let's just talk about this mean value theorem here. We have our coordinate system, we have our function, and what a nice smooth function it is. Here's its graph. Here's A and B on the x-axis. A is less than B. We have these points A comma f of A up there on the graph, B comma f of B up there on the graph as well. We draw this line from here to there. We call that a secant line for some reason. And what happens with the mean value theorem is you can parallel transport that line till it last intersects the graph. And there it happens is the tangent line of the graph is of the same direction as your secant line. And with appropriate hypotheses, that can be proved always to happen. So, let's take a look here. Does this work? Let f be a function with real inputs and real outputs. Let a and b be real numbers with a less than b. Assume that f is differentiable all throughout the interval from a to b. All throughout here, a tangent line will exist if graphed. And assume that f is continuous at a and b, that there's no funny business happening at the endpoints here. Then there exists a real number c between a and b, so that the derivative of f at c, which is of course the slope of the tangent line, is the rise over the run of that secant line, the slope. There's the mean value theorem presented for you. And this we call informal exposition. Let me move over here. So that's not looking bad, is it? You'd think that mathematicians would be able to formalize that without making a mess of it, but let's see what happens. So, in traditional statement-oriented formalization, also given the name Frege-Hilbert syntax, we get this. I'm not even going to read it. Okay, it's unreadable, both orally and almost unreadable in any sense of the term readable. It's got these nest levels. Everything has to be nested because the syntax does not accommodate flowing phrase structures. And you have this. If this is the product we're selling, there will be precious little demand for mathematical logic or for mathematical logicians. Now, this expression is in the ground language of mathematics. We've made a lot of to-do about the division between ground and meta-mathematics. The phrase structure of this expression is entirely nest-knotted and user-hostile. Furthermore, the applications of rules of calculus are a terror to try to make any deduction inside the system. In an earlier presentation, I talked about the mind-boggling nature of the proofs of Gödel's first and second incompleteness theorems. Part of the mind-boggling nature is the idea of dealing with such extremely user-hostile expressions, in addition to all the other things that are going on in the proofs of those theorems. So, that's the ridge we are on. I hope you want to get to the next ridge over after seeing that, and you can imagine the monstrosities you get with other things. So let's start over. Here's the informal presentation given. We use standard constructions. Let f be a function with real inputs and real outputs. Let a and b be real numbers so that a is less than b. For all x between a and b. We'll just do various rudimentary things. We aren't really on the next ridge at all. Looks like we're already on this one. But we're transitioning a little bit. This is a for all. That's surely a for some. Oh, we have a qualified quantifier here. There exists a real number c, so that c is between a and b, for which the slope of the tangent line is the slope of the secant line. Here it is. At small scale, the two ridges are much the same. you can't see that we made any progress. But let's formalize at middle scale. Here we have this. Ooh, let at middle scale is an upside down A. Or, in sans serif dialect, sans serif A. Let f be a function. Ooh, here's another let. Oh, and we've got a qualified quantifier at middle scale. Let A and B be real numbers so that A is less than B. Assume that's a G clause at middle scale when given that this is true. When given that for all real numbers x between A and B, f is differentiable at x. We're also going to assume that f is continuous at A and at B. When given that f is continuous at A, when given that f is continuous at B. Here we see a then in middle scale. That's an R clause. So we put in R clause. We've turned it back to the sans serif dialect again with a sans serif C. There's our qualified quantifier. And we terminate the string with Boolean truth, which from the last presentation is the final remaining statement-oriented logic in this context-oriented system. We're back. The technology, does things. So, this is what we have. We have formalized at middle scale. Now, we can do a touch of context-oriented simplification. There's a calculus. It's very easy to see that this next thing is tautologically equivalent to what we've just had. And so look at that. We have these clauses flowing one after another. The next level is now 2 because of what's there. Yeah, that's it. That jacks the maximal S level up to 2, but pretty much it's flowing at a nest level 1. Well, there's another scale. Let's formalize at large scale. Here it says theorem. That must be a large scale R clause. So we put this R clause with its opening brace there, its closing brace there, and the mean value theorem is there. We add a comment with the mark operator. R is already means required, so we can't have a remark operator. So we use some old-fashioned English. Mark that this is called the mean value theorem. And here we have it. Now that's well structured. Let me just talk through this a little bit. This is all in the ground language of mathematics, but it's definitely not Frege-Hilbert syntax. There's not a meta thing on this board. To establish context-oriented mathematical logic, of course, requires a lot of work in the meta language. Just as to make a clock, you've got to go to the clock shop and read the clock first. But this is all now in the ground language. Let me discuss the phrase structure of the expression. You see ramified, diversified ramification. We see a substantial nest here. Yes. We see a lot of flowing structure inside this nest. We have these clauses coming one after another. This such that comes after for all, and so it's really a given. That's an hypothesis, not a conclusion. This such that after the existential quantifier is an R clause, so this is required that C be between A and B. Then concatenation is the constructed form for context. I can take any comma here, add, stop. Oh, please. I think I know how to make this thing. Oh, my word. This thing. Okay. I guess I can't touch it. Okay, it's untouchable mathematics. So now I can conceive of this up here as a context. Maybe that would all be a context.
A lot of people would think of this down there together with that Boolean truth there to make a statement structure out of it. However, you can divide it at any point. Think of the stuff above it as context, the stuff below it as statement. You can vary the amount of context orientation and statement orientation you wish to use in this system. Then, these contexts have a scope. Contexts do not in general have inverses. So here we see it's an hypothesis that A is less than B. That hypothesis has force all the way down here, but is terminated by this brace set of the next scale up. So contexts have not inverses, but you can turn them off en masse with a closing brace set at the next larger scale. Now also the application of rules of calculus is also very user-friendly and easy. So if we had something from a prior theorem that's called a copy migration rule, you can take that and copy it and get it towards here and then work with your calculus. And the calculus feels like symbols in motion. Rather than plugging this in for that, there's a dynamic feel to the entire calculus in the context-oriented system. Context-oriented mathematical logic is just mathematical logic done in a new way, but may well be logic as it always should have been. Machine partially formal systems do not have to be relentlessly user hostile, and that is why this author of this book, which is the same as the presenter, calls this a paradigm shift. That the vast bulk of people at this time think that all formal logic and all formal languages must be extremely user hostile. Well, they don't have to be. You've already seen an example. We have seen how the new formal linguistics can be used to create a system in which formal logic can be made to fall into pliant, easygoing, and user-friendly forms. With the machine partially rigorous calculus for this logic also being pliant, easygoing, and user-friendly. It's my opinion, and I hope it is yours as well. This new system fully warrants the name it has been given, well-structured mathematical logic. Thank you, Mr. Chairman. My presentation is ended.
Thank you very much, Dr. Scott. Ladies and gentlemen, that concludes today's presentation. Please let's give a warm and glowing send-off to Dr. Damon Scott. Thank you very much.
Welcome back, everyone. My presentation was ended, but a member of the audience had a question, and I thought the question was so important that I'm going to answer it for everybody here. So the question was whether this stuff about f being differentiable at x is part of the meta language, and maybe we're doing some meta stuff here. But in fact, it's all in the ground language. So let me describe this. This is a large-scale R clause. Above this, in our theory, would be a large-scale G clause, given that f is differentiable at x if and only if and all those epsilons and deltas. So that would be the definition. Definitions show up in the language at large scale, usually with a G clause, but maybe for all you'd have to work it out. So that's how it works out. Then you could also put all those epsilonics right here in this spot. We saw last time that the epsilonics flow, they do not nest. And so the entire expression will become now much longer, but it will not become more nested, which again blows the minds of all the people who have ever thought of formal languages up to this point. Similarly, we can do this. F is continuous at A, and F is continuous at B. It had also been noted that some presentations take the ground language to be extremely low level. That if then, oh, that's not in the ground language, you have to say or, I forget, P, not P or Q, whatever. And it has to be translated all the way down there. One way to think of it is
assembly language or machine language for a computer. Some would say to be a computer programming language, ground level has to be machine language or assembly. We don't do that. C, Fortran, your software packages are all in a computer language. So that's another reason why this is all in the ground language, even though it does use some fairly sophisticated operators. Thank you. Have I answered your question? Okay, he says I have. Thank you again, everyone.